This is the third of 3 lectures on Chapter 6, Applications of Newton's Laws. It will focus on circular motion. An object moving in a circle must have a force acting on it. Otherwise, it would move in a straight line. The direction of the force is towards the center of the circle. This is called centripetal force. Note, we sometimes mistakenly call this centrifugal force because we feel pushed outward. That feeling is really your sensation due to your inertia or tendency to travel in a straight line. Algebra gives us the magnitude of the acceleration and therefore the force required to keep an object of mass m moving in a circle of radius r. The magnitude of the force is given by Fc equals m times ac, or m times v squared over r, where v is the tangential speed and is the circumference divided by the time for one revolution. To find the acceleration of a 20 kilogram mass tied to a 2-meter string that is swung horizontally at 20 meters per second, we simply plug into the centripetal acceleration formula, where AC equals v squared over r. Make sure everything is in meters and seconds. Doing this, we get an AC of 200 meters per second squared, and the acceleration is always towards the center. The centripetal force is just Fc equals m times AC. So plugging in for mass, we get a centripetal force of 4,000 newtons, directed towards the center as well. Now consider a car rounding a flat curve on a road. The only force pushing the car into the curve is the force of static friction. So the static friction has to be equal to the amount of centripetal force needed to keep it in the curve of whatever radius and at whatever speed the car is traveling at. Once the car goes too fast, static friction is overcome and cannot push the car into the circle. The car skids tangent, and now kinetic friction is acting on the car, which is an even lower value than that of the static friction. So the car will go tangent to the curve. A 1,000 kilogram car is traveling at 28 meters per second on a curve of radius 30 meters. What is the centripetal force acting on the car? To calculate the centripetal force on it, we use the formula Fc equals mv squared over r. Plugging in, we get 1,000 kilograms times 28 meters per second squared divided by 30 meters, which gives us 26,000 newtons. What frictional force must be acting on the car? The static frictional force has to be equal to Fc, so we can set Ff equal to Fc. To find the coefficient of static friction, we can solve for mu. Ff equals 26,000 newtons. It also equals mu times mg. Mu is equal to 26,000 newtons divided by 1,000 kilograms times 10 meters per second squared, which gives us a mu of 2.6. So remember that mu will change depending on weather conditions. So if it rains or is icy, there will not be enough friction to keep the car on the curve at this speed. So a better way to build a curve on a road is to bank it. Now the force that actually pushes the car into the circle is not friction, it is the normal force. This means that the road can be designed to have the right banking angle, so it can always provide enough force to push the car into the circle. The banking angle only depends on the speed and the radius of the curve. It is completely independent of the mass of the car. So a Prius or an 18-wheeler can safely travel at the recommended speed around the curve.